I would like to continue our exploration into creativity, now focusing on mathematics. Quantum computing, artificial intelligence, and augmented reality will radically reshape the future. But why now? What's been holding these technologies back? I believe the main rate limiter for these technologies is the availability of creativity. It's creativity that will make these technologies omnipresent in every aspect of business in the future. But first, a bit about quantum computing. In conventional computers, circuit behavior is governed by classical physics, the laws of physics launched by Isaac Newton 350 years ago. CMOS transistors are the basic building blocks of conventional computers. In quantum computers, circuit behavior is guided by quantum mechanics, the physics initiated by Albert Einstein 100 years ago. Superconducting quantum interference devices, or SQUIDs for short, are the basic building blocks of quantum computers. Conventional computers restrict the information to a binary 0-1. They are either up or down, open or closed. Quantum computing uses qubits that can be entangled and present in multiple states at once. A quantum computer could watch 100 billion security cameras at a time, but that's not useful unless there is an algorithm that can detect what one might be looking for. Algorithms are the backbone to computer programming. It's the creativity of mathematicians that has given us most of our algorithms.
There are so many different types of mathematicians. Some of them are really rational. They don't believe in God, they don't believe in wonder. So they just proven theorems according to the rational way of thinking. And probably this is the most of mathematicians are this way. But Ramanujan is quite different. He says that his creativity comes from an Indian goddess. So
many associate creativity to an aha moment, or something just pops into your head. A revelation, an hallucination, an epiphany, a prophecy, a vision, an inspiration. Einstein described an aha moment when he modified his equations to treat time as a variable. Joseph Smith experienced a vision in the woods that launched the Mormon religion. Archimedes, after realizing that different materials displaced different amounts of water, ran through the streets shouting, "Eureka!" I want to add one more aha story, highlighting mathematicians.
This is essentially what we do.
Mm-hmm.
Come up with ideas and then, turn them into actual work and, if possible, papers.
Mm-hmm.
And but of course, the whole process is quite complicated. It's not one thing; it's a lot of things.
Let me tell you my own experience.
Yeah.
I can work for months around something and not get it. Think I'm close, but just not get it.
You have to have some trust in yourself and be willing to fail. And not beat yourself up over it too much.
There's an objectivity in it.
Yes.
So math is tough,
Yes.
and it's hard to get creative.
You have to bash your head against the wall or against the problem. And you're working within certain constraints, and that gives you a hint of how to move forward if you're working within a certain constrained system. So it's better not to have too much space when you're first thinking about a problem.
So this is the kind of timeline. I would say a very long process of waiting, and then boom, suddenly it comes. It looks more like that.
Uh-huh. And what is that? What is that? This is
So let's
unconscious,
see,
or is it
I
someone
think
says the right word to you, or what?
So what happens here?
Yeah.
I think here happens the fact that you have tried all these things, and maybe several times. You see, there's a question of memory effect.
Yeah.
When you're here, you already forget what you tried here, so you're trying it again. And then you figure, oh, I've seen that somewhere already.
Mm-hmm.
But then it's not always exactly quite the same way in which you approach the thing. So it's like you have to, you have your hammer and you dig and you dig and you dig. And eventually, when you reach that point here, there's a little thing that you never thought about all this time, right? Which suddenly, pops up.
Mm-hmm.
And then it's your
Yeah,
job is
yeah.
to realize that this is
Yeah.
the thing.
And then if I want to approach a new problem, then I have to come in with from a different context and have a slightly different way of thinking, and then I can really contribute to solving a problem that hasn't been solved by the people that usually work on this problem. So I have my own way of thinking, but I need to approach from a different direction, right? So that I can solve something new, so that I can contribute something.
I asked Philippe to illustrate one of his most important mathematical accomplishments, or better known as solving a proof.
So what we're going to do is fold this strip of stems so that it takes the smallest possible place. But of course, we don't want to destroy it. So we have to fold onto one stem, basically. So let's try with it. And of course, we want an interesting folding, something that's, wow. Okay, so this is my folded strip of stems. So the mathematical problem here is to try to count in how many ways I can fold my strip of stems. And I can tell you with 12, it's really a very large number. So
Maybe we should do it with 2 or something to start with.
that's a good idea, but you won't see the nice trick. We want to create an object that will be kind of easier to apprehend, okay? So this is kind of one-dimensional, right? It was a one-dimensional strip, and now it's folded onto a zero-dimensional object, which is this completely crushed object. Now, what we want to do is, on the contrary, extend it and make it look two-dimensional. So in order to do that, I'm going to pierce my strip of stems, but it's going to... This object is called a planar map. So why planar? Because I'm putting it on a flat surface, okay? And it represents a certain configuration, a picture, and this configuration is that of a straight river and a winding road crossing it through a fixed number of bridges, which in this case is 12. Now we have our favorite field theory, this -4 central charge field theory coupled to fluctuations of my space-time. Okay. And thanks to the knowledge of this theory, we are able to compute things. And what we're going to compute is actually the asymptotics of a number of such possible configurations. Mm-hmm. But you have to remember, all such possible configurations are all the possible configurations of a compactly folded strip of stems. And that number we computed, and the value of this number is 12 plus square root of 1/145, the whole thing divided by 12. Evaluating the number of ways to fold a strip of 2n stems when n becomes very large. Voilà. So that's the whole story.
The idea itself comes from intuition, I think. It's also in the mathematics the case. It comes from intuition. That you know, mathematicians are sometimes just ahead of their time. And maybe one of the best examples in the history of mathematics, if you're allowed to, is the invention of the Riemannian geometry. Everybody heard about the Albert Einstein and general relativity. So it's well. And Albert Einstein came and found an application in physics for that. So I think it's one of the most famous stories in the history of science, illustrating this fact that mathematical equations have to wait maybe a couple of years until they get discovered by physicists and they got applications.
The segments that will most benefit from quantum computing are financial modeling, drug design and development, logistics operations, materials research, and climate and weather forecasting. All these problems have a fundamental question. How many possibilities are there anyway? Creativity in mathematics offers the purest moments of insight. A prophet can think it was God, but cannot prove it. A scientist can point to a huge body of data, but that does not make the theory true. Mathematicians have the luxury of being able to prove their insights are correct.
The idea is to rewire your brain. So if you try really hard to work on something, eventually your brain becomes used to thinking about that particular problem and will become rewired.
When it comes to aha moments, mathematicians have the most pleasure.
So there's also a question of, pleasure, creation of happiness out of this. So you have all this hard work, like depression almost, and then suddenly, and then you know that all this hard work was useful. Okay?
It's really, really tremendous joy and triumph and energy which fills you after you have finished a proof.